Okay, it's 10 o'clock. We'll get started. Hello, and thank you to everyone around the world for joining us for this week's lab meeting. My name is Kristen Abood. I am the science editor at the Human Vaccines Project, and I will be your moderator today. Once again, the news this week centers on the Delta variant of SARS-CoV-2, the most transmissible and formidable variant of the virus to emerge so far. It continues to account for spiking case counts, particularly among those who are unvaccinated. A study from China suggests that individuals infected with the Delta variant have about 1,000 times more virus in their respiratory tracts than those infected with the original SARS-CoV-2 strain, which likely accounts for its increased transmissibility. In response to surging cases, countries are enacting new restrictions on indoor activities and travel and reinstating mask and social distancing requirements. Over the weekend, France began requiring proof of vaccination or a recent negative test result for admission to many indoor venues, including some bars and restaurants. In Pakistan, unvaccinated individuals over 18 years old will no longer be allowed on domestic airlines. This week, the US Centers for Disease Control and Prevention also urged all Americans, even those vaccinated, to return to wearing masks indoors in areas where the virus is surging. And while the COVID situation has improved in India and South America, former hotspots, Botswana, Kazakhstan, Malaysia, and Spain are among the countries with the highest infection rates in the world, according to the latest data. All of this illustrates just how far any country is from being finished with COVID-19. Before we begin today's presentation, I just wanted to note that some of the information presented today is currently under peer review. At the request of our speaker, we ask that you not reproduce or disseminate the data that's presented. This session will be recorded and made available on our website and our social media channels for you to review. And with that, I am happy to introduce today's speaker, Dr. Stanley Plotkin, veteran vaccine developer and founding board chair of the Human Vaccines Project. Dr. Plotkin is an emeritus professor of the University of Pennsylvania and an adjunct professor at Johns Hopkins University. He also serves as a consultant to many vaccine manufacturers, biotechnology companies, and nonprofit research organizations as principal of VaxConsult. Dr. Plotkin has had a long and successful career in both academia and industry. He developed the rubella vaccine, now in standard use throughout the world, is co-developer of the pentavalent rotavirus vaccine, which is used in the US and elsewhere, and has worked extensively on the laboratory development and application of already licensed vaccines, as well as others in development, including anthrax, oral polio, rabies, varicella, pertussis, Lyme disease, and cytomegalovirus vaccines. He has received numerous international awards and accolades from medical and scientific communities and has edited several books, including the standard textbook on vaccines, now in its 7th edition, entitled Plotkin's Vaccines, which I think pretty much says it all. During the presentation, please send me your questions using the Q&A function in Zoom. I will ask our speaker a broad selection of your questions after the presentation, and we will have about 25 minutes for discussion. It is my pleasure to now introduce Dr. Plotkin.
Well, thank you very much for that kind introduction, and it's great to return to the Human Vaccines Project, which I certainly admire. So my talk today is going to focus on correlates of protection by vaccines, and it's divided into 2 parts. One is, the first part is general principles on this important subject. And the second part specifically will focus on SARS-2 correlates of protection. And so why are correlates important? Well, you probably all know this, but of course, basic immunology, we want to know about these things. But it enables us to correctly choose the antigen in a vaccine that will work, that will give efficacy. It enables consistency of potency to be monitored in vaccine manufacture. It allows us to determine the susceptibility of an individual person or a population. And also, in some cases, if efficacy trials are not feasible, immunological data may enable the licensure of a vaccine given a correlate of protection. And it also enables bridging from first generation to second generation vaccines. Next slide. So terminology is important in this area. A correlate of protection I define as an immune response that is statistically interrelated with protection. That's the basic definition. Now, you may have an absolute correlate, that is to say, a specific level or titer that is highly correlated with protection. So a threshold. However, in many cases, the correlate is relative. That is, a high response is more related to efficacy than a low response, but there are exceptions. And then, importantly, there may be more than one factor that correlates with protection. Next slide. And it is also important, although maybe not so much in this lecture, to distinguish a mechanistic correlate, that is to say, the biologically responsible immune response that correlates with protection. And next slide. A non-mechanistic correlate, that is sometimes called a surrogate, that is an immune response that substitutes for the correlate of protection, the true correlate, but that correlate may not be easily measurable or may be unknown. Next slide. So this slide is not to go into detail, but to point out what is obvious, and that is that there are many different immune responses that can be correlated with protection. And this slide is certainly incomplete, but simply to point out that both serum and mucosal antibody may be important, and of course, T cells have many different functions which could be correlates of protection. Next slide. So let me go through some principles and use examples. So the first point is that you have to define protection, the correlate against what? It might be that you're looking for a correlate against infection or a correlate against disease. And within those categories, you may have correlates against local infection or disseminated infection, and also correlates that may be useful for correlating against severe disease or mild disease. And a good example of this is polio vaccines. We know that the oral vaccine protects against infection, whereas the inactivated parenterally given polio vaccine only prevents against disease. It does not prevent infection, at least in the intestine. So that is, polio vaccines are a good example of the importance of defining protection exactly. Now, next slide also points out that that for pneumococcal vaccines, we can prevent bacteremia. And this is a gross generalization because it differs according to serotypes, but generally speaking, one needs a much lower level of antibody to prevent bacteremia, pneumococcal bacteremia. But if you want to prevent pneumococcal carriage or otitis, the vaccine has to deliver higher titers in order to do that. So that's the first principle. Next slide. The second principle is that the mechanism of protection against infection, that's a mistake there in the slide, is not necessarily the same mechanism as recovery from infection. And this is a quite an important principle. Next slide. This is illustrated in a way by the measles vaccine, that it has been demonstrated that higher levels of antibody response to the measles vaccine not only prevents measles, it also prevents infection, which is great. The next slide shows that T-cell deficient humans, if they get measles, suffer serious and fatal disease, which also can be demonstrated in monkeys, that monkeys depleted of CD8 T cells have increased viremia, and the result, of course, in some cases, is serious disease. So the point here is that you need, in the case of the measles vaccine, you need both B cells and T cells. B cells to prevent infection, and if you do get infected, T cells to control infection. Next slide. Now, a large challenge dose can overcome immunity, and you know, I think we're probably seeing this with the Delta variant of SARS-2, that even people with vaccine-induced titers can be, in some cases, infected when their titer drops. I'll come back to this later in the talk. But the point, again, is that the challenge dose does matter. And of course, as you can imagine, protection is better against small challenge doses than large challenge doses. So that is an important principle to keep in mind in the second part of this talk. Next slide. So the fourth principle is that most current vaccines protect through antibodies. I'll come back to that briefly later. But in fact, we have very few vaccines that act principally through T cells. Of course, for many vaccines, T cell responses are important. But in terms of key responses, the BCG vaccine and the zoster vaccines are really the only ones for which T cell responses are the key correlates of protection. So this is, I think, an important philosophical point. We have to deal better with diseases where cell-mediated immunity is important. Next slide. Next slide is really meant to show that because most of the diseases for which we have vaccines act through viremia or bacteremia, the importance of serum antibody is obvious. But also mucosal antibody may be important, is important, for example, with influenza, with rotavirus, with human papillomavirus, and serum antibody, of course, may bathe the mucosa and thereby protect. But unless that happens, mucosal infection may occur even in the absence of general infection. And of course, toxin-producing bacteria are prevented by antitoxin. Next slide. I think I'll skip that and move on to the next slide. So the fifth principle is that correlates may be relative. I've made this point before, but I just want to illustrate it. Next slide. With pertussis. because obviously we have both whole cell and acellular pertussis vaccines, and they both work, at least to some degree. But when you try to establish a correlate of protection, one finds both in household exposure studies and non-household exposure studies that the higher the antibody, the better. Certainly for complete protection against infection. But as antibodies decline, vaccinees may get mild infection. And as antibodies decline further, they may even develop severe infection. So here is where the correlate of protection is definitely antibody, but may vary considerably. Next slide. Now, the sixth principle is sort of obvious, that antibodies must be functional. Next slide. And a good example of that is with a study done with the Group C meningococcal polysaccharide vaccination, where the vaccine gave ELISA antibodies through all the age groups. As shown in this slide, even one-year-old children, when injected with the vaccine, developed ELISA antibodies. But they did not necessarily develop bactericidal antibodies. And as you can see from the slide, the efficacy under age 2 was essentially none. Whereas as vaccinees aged, with increasing age, there was more bactericidal response, and adults were reasonably well protected, whereas children were only moderately or not protected at all because of the absence of functional bactericidal antibody. Next slide. Now, the next principle is that, more than one factor may protect as co-correlates. I'm not going to illustrate this necessarily, but simply to point out the obvious point that both antibodies and cellular responses may be important for many vaccines. Next slide. Well, okay, I guess I will illustrate this with the live influenza vaccine. Here the point is that, as you might imagine, if a child was given the vaccine and had neither a serum response nor a nasal IgA response, the individual on challenge with the live vaccine could be infected. Whereas at the bottom of the slide, children who developed both serum and nasal IgA antibody were well protected. But individuals with either serum or nasal IgA were moderately protected. So in this case, the two responses were synergistic and necessary for the best protection. Next slide. And I'll skip that slide, move on. So the next principle is that memory may be a mechanistic correlate. And the best example of that is hepatitis B vaccine, where about half of vaccinees vaccinated in childhood will lose a detectable antibody by the time they become adults, and yet protection persists, has been shown to persist for at least 20 years because of memory responses. Next slide. And as far as T cell responses are concerned, next slide. Again, we have examples with tuberculosis, as I mentioned, with BCG vaccine, but by and large, and talking now specifically about cytotoxic T cell responses, they are not protective against infection, but influence the course of disease. And so the last principle is that there are non-mechanistic correlates of protection that are useful. For example, next slide, the zoster vaccine, where the recombinant vaccine based on the GE protein plus an AS01 adjuvant gives very high efficacy, but the correlate is really CD4 T cell responses. Nevertheless, as obviously, it's more difficult to measure those, and antibody can be used as a correlate, but it's not the mechanistic correlate. The T cell responses are the mechanistic correlate. Next slide. So I just want to mention in passing that when you get to intestinal pathogens, you have a whole range of factors that correlate against protection. I'm not going to go into this in detail, but obviously mucosal antibodies are important, and other innate responses. Next slide. The last point in this part of the talk is just to give the example of influenza vaccines and their complexity in terms of correlates. We use the hemagglutination inhibition titer as a rough way of correlating against protection, but microneutralization may be better, but even microneutralization isn't perfect. We know that antibodies to neuraminidase contribute. We know that ADCC antibodies also contribute to protection. We know that mucosal IgA helps, certainly for the live influenza vaccine. And lastly, we know that CD8 T cell function is important in the elderly for protection. So let me now move to SARS-2 and make some remarks about the correlates of protection. This cartoon of the virus is simply to point out the different proteins on virus, which by this time everyone has memorized. The spike glycoprotein on the outside, the nucleocapsid N protein on the inside, and also two important antigens on the surface of the virus that are not talked about much: the membrane glycoprotein and the small envelope glycoprotein. So there are more antigens than the spike glycoprotein, despite our largely focus on that particular antigen. Next slide. So as we all know, there are many vaccine platforms being developed or have been developed against the SARS-2 virus, both inactivated vaccines, even a live vaccine in development. We all know the use of adenovirus vectors and also other vectors which have not been as useful thus far to develop vaccines. And the next slide shows that there are also protein subunit vaccines as well as the nucleic acid vaccines. So, you know, this is a terrible thing to say, perhaps, but this last couple of years have been terrifically advantageous for vaccinology. We have learned a lot, despite the death and disease and economic destruction that is going on around us. And much of our knowledge will be useful against other vaccine targets, as is obvious from the work going on in many different laboratories and pharmaceutical companies to use the knowledge gained with SARS-2 to apply to other vaccines. But I want to talk about the correlates of protection against SARS-2. And this is work done by David Goldfarb, particularly in the United Kingdom, but with the help of many different people. And I'm just the, what shall I say, a helpful observer in these studies. But anyway, here are data against the original SARS-2 isolate for a number of different vaccines. Novavax, the Pfizer vaccine, the Moderna vaccine, Sinopharm, the Oxford AstraZeneca vaccine, chimp adeno, and a Sinovac vaccine. So the point of this slide, to take you through it, is that the data on the right side for each graph are titers, neutralizing titers, taken from convalescent humans. So in other words, humans who have had SARS-2 infection and have successfully lived through it, and those are the titers that they have. And the reason for measuring those is because they are a useful correlate of protection. And what you see for each graph for the pre-vaccination and then post-vaccination are the titers that are seen in vaccinees. So on the left part of the slide, you see that the mRNA vaccines and the Novavax vaccine produce relatively high titers in relation to the human convalescent titers. And you see at the bottom the efficacy against the original isolate, original SARS-2 strain. And you can see that the titers are rather high for those vaccines in relation to the convalescent, and that the efficacy is also high. As you look at the other vaccines, you can see that in relation to the convalescents, that their neutralizing titers are considerably lower. And you can also see at the bottom that their efficacy is correspondingly lower. So this then is the principle that neutralizing titers do correlate with efficacy. Next slide. I'm going. This slide lines up the titers. On the x-axis shows the neutralizing titers, and the y-axis shows the efficacy. And you can see how the various vaccines line up. Now, the left graph shows neutralizing titers. Okay, so obviously that's a specific test. And just to explain the Oxford AZ 2 points, the slide shows the data from Oxford with longer interval between the doses, because that matters. Priming does matter. But aside from that, if you look at the right side, the right graph, you see ELISA titers, in other words, not neutralization, but measurement of antibodies grossly, in a sense. And you see that there is a better correlation actually with the ELISA titers than the neutralization titers. And this argues, I think, that antibodies against the RBD are not the only protective factor, that antibodies against other parts of the spike, notably the NTD, do influence efficacy. Next slide. I'm going to skip that. The next slide after that shows the importance of interval for the Oxford Zeneca vaccine. This is a principle which should be obvious because it's true for many other vaccines as well, that the longer the interval between doses, the better the immune response. And the British recognize that and have lengthened the interval between the two doses to 12 weeks. And you can see that for good reason. And this explains why we now need booster titers for the mRNA vaccines, because the interval between the two doses, from the point of view of immunology only, was too short. And a booster dose at 6 months is going to give a much better response. Next. Well, this just shows the data in another fashion, but also mentioning other vaccines. And the point is that even for the vaccines that are less effective, they induce lower titers. So the relationship between antibody induction and efficacy is solid. And in my view, there is no doubt that antibodies are the correlate of protection, measured by neutralization or measured by ELISA. Next slide. But of course, one shouldn't forget T-cell responses. And these data show that responses in disease after SARS-2 infection include responses to multiple antigens, not only against the spike shown on the left part of the slide, but also to the two antigens that I mentioned, the E and M, and also the N nucleoprotein. And so if we need T-cell responses, we're going to need, I think, more than the spike. Next slide. And this shows, in particular, CD8 T-cell responses. The data suggests that CD8 T-cell responses are important in controlling replication if infection does occur, and in inducing milder disease. And what this slide points out simply is that the nucleoprotein is the best inducer of CD8 T-cell responses, which might argue that the N protein should be included in vaccines. So coming to the end, next slide, just repeats what I said before, that if you look up the various vaccines, the mRNA vaccines on the left, the Novavax vaccine in the center, and the two adenovirus vaccines on the right, that their spike antibody correlates very well with their efficacy. And therefore, that can be used as a predictor of vaccine efficacy for the new vaccines that are being developed. The next slide speaks about things that we don't yet know for certain. I think that, as I've just shown you, that CD8 T cell responses are important, but there's still argument about that. My view would be that the RBD is important, but I don't think it's sufficient for antibody induction, and I would recommend that RBD not be the only antigen in a vaccine. Obviously, the duration of antibody responses is key. It looks, unfortunately, that the mRNA vaccines do not elicit very durable responses, and that boosters are going to be needed. And then, of course, the question of mucosal responses. It appears, as a generality, that the more serum antibody you have, the more mucosal antibody you have, and that therefore vaccines with higher antibody induction are going to also better control mucosal replication. And the last slide points out that we still have a problem with the elderly. The responses are definitely lower to all of the vaccines in the elderly. We don't know about vector immunity. In other words, to the adenovirus. Is that going to become a problem if one wants to boost people? And of course, the next question I would answer is definitely yes, that decline in immunity will lead to more infections. And as far as COVID-19 becoming endemic, at this point, I think the money would be on the answer being yes. And as far as mutations are concerned, I don't yet see a stop to that. So that may be a negative conclusion. But on the other hand, I think that we can adjust the vaccines to meet the challenge of mutation, and the indication that booster doses will cover the mutants better than the original vaccinations is also a very favorable observation. And I will close there, and thank you very much for your attention.
Thank you so much, Dr. Plotkin. That was really a wonderful presentation, and I feel so honored to have you to share all of your wisdom with us. So thank you so much. So we have quite a few questions in the Q&A. The first one, more general question. How do you distinguish between a mechanistic correlative protection and a non-mechanistic correlative protection?
Well, so the example that I gave, the zoster vaccine is probably the best example. And so the question, of course, is how does one, how do you distinguish? And the answer is simply you look at the correlation. In other words, people who get zoster after vaccination, have they had declining antibody, declining cellular responses? And it appears from the data collected by the vaccine manufacturers that the cellular response was more important. Of course, you could sort of guess that from the fact that zoster is the recrudescence of varicella, and from being latent in the ganglia, and chances are that cellular responses would be involved in suppressing that. But aside from guessing, you simply measure the correlations between the two responses and breakthrough disease. That was particularly well established with the Merck vaccine, because with the GSK vaccine, there have been fewer breakthroughs, but with the Merck vaccine, there were many breakthroughs. And so it was easier to measure the correlate.
Right, right. So could you comment on what vaccine platform has the most potential for the development of next generation broadly protective influenza vaccines?
Ah, boy, that's a big question. And I wish I really knew the answer. I do think that we are going to see messenger RNA vaccines for influenza. And the question will be exactly what is the breadth of the responses induced by the mRNA in relation to the current inactivated, or for that matter, live vaccines. Because as we all know, the problem is that once you are infected with influenza early in life, your response to vaccines is forever influenced by that original infection. So the problem is the breadth of the response to the vaccine. And although I cannot predict, but I would hope that that the breadth of response to either the mRNA or the adenovirus vectored vaccines would be broader. That's a hope. I don't know if that will come to pass or not, but it might make at least adaption to a new variant quicker than it has been in the past. So in other words, one could make the vaccine or adjust the content of the vaccine more quickly with those technologies.
Right, right, absolutely. So you clearly talked about the duration between the prime and the boost having positive impact. What is your opinion about mixing a vaccine platform, so the heterologous prime boost, to enhance durability or the breadth of immune responses?
Well, the data are not yet completely in, but it looks to me as if it's not going to make much of a difference. In other words, that no matter which boost you use, you're going to get a good boost. Now, I shouldn't say that with certainty, because, as I just said, we need a lot more data on that point. But the data that I've seen thus far lead me to optimism that it's not going to matter a great deal which vaccine you use as the booster. But
Right.
that boosters will be needed, I have no doubt.
So related to that, we had a question specifically on why, if you had any sense as to why Pfizer is pushing for a third shot, a booster dose, and Moderna has not come out on that issue. And just curious if there's any scientific explanation for that.
Well, the only answer I can give is I haven't seen the data on the Moderna, so I don't know what they show, but the data shown by Pfizer are very convincing. That is, the titers fall considerably by 8 months, what are the data that they've published. And I think they're absolutely right that a booster is going to be important, because the titers fall to levels which are about the same as the inactivated vaccines, and we know that they are less potent. So, and of course, we've heard data from Israel that people previously vaccinated with mRNA are getting infected. So I don't think there's any doubt. that a booster is needed, and likely will be true for Moderna as well as Pfizer. And I personally regret the attitude of the ACIP and not beginning to recommend the booster, because I think it's obvious that it's going to be necessary. That being said, the disease that will occur in those not boosted is going to be mild, definitely milder than the disease in non-vaccinees, because they will mount an anamnestic response, but you need a quick anamnestic response. And so I definitely believe that the data argue for a booster of the Pfizer vaccine. And fortunately, the responses are phenomenal with the booster.
Right. Yes. So related to that, with the inactivated, we have a question on whether you believe that the Sinovac vaccine still has a role in vaccination programs.
Well, considering that there are billions of people not vaccinated, I think any vaccine has a role. Obviously, it's less effective after the first 2 doses. It may be that a booster will do something for that vaccine, but at least I think there's a chance that it will modify subsequent infections sufficiently so that there will be fewer deaths and serious disease. So let me put it this way. If I had a choice between which vaccines to take, I would not choose the inactivated virus vaccines. But if I'm in a place where I have no choice, I would definitely choose to get that vaccine. And the question will be not so much a scientific question as a practical question. How many doses can be made where and disseminated to where? And considering the billions of people who are not vaccinated, I think any vaccine is better than none.
Yeah, absolutely. Absolutely. So with regard to the mucosal immune responses, would you comment? We have one question about the oral vaccines for SARS-CoV-2, and would they have the benefits of having mucosal protection or a nasally administered vaccine?
Yeah, well, so that's the hope, and we don't have the data yet, but that is certainly one reason for considering a nasal vaccine. That being said, the data from monkeys and from humans, but there'll be a paper published in the New England Journal soon about monkey experiments showing this, that that mucosal immunity is secondary to systemic immunity. In other words, the levels of antibody required to protect the lungs are lower than those to protect the nose. So the higher the titer, the less nasal infection there will be. But of course, the disease, the serious disease, is occurring in the lungs. So I guess what I'm saying is that lower levels of antibody are going to protect better against serious disease. They may not prevent infection of the nasal passages very well, but even if they decrease the amount of virus in the nasal cavities, that's important epidemiologically. So I wouldn't sneeze, so to speak, at vaccines that don't prevent nasal infection as well as they prevent infection in the lungs.
Right, absolutely. So one question on your comment on boosting with the Pfizer vaccine, does that suggest that B cell memory alone will not be sufficient for protection? Because there has been some reports about the sort of B cell memory being reported and identified. So do you think that maintaining circulating antibodies is required?
Well, the problem is that the incubation period of the infection, as we know, is 5 days or less. You know, it averages to less than 5 days, but that's pretty quick, and that doesn't allow the immune system to fully respond within that time. So reinfection is possible during that period. And what I think we know is that the higher the titers in the serum, the higher the systemic titers, the more perfusion there's going to be in the nasal cavity. So by that reasoning, the higher antibody you have, the less likely you are to have virus in the nasopharynx and to transmit it to others. So that's another argument, if you will, for choosing vaccines that give high titers, or boosting vaccines to give high titers, so that you have an epidemiologic effect as well as a personal effect.
Right. And so, given that the elderly response to vaccines may be lower, and the elderly in the US were given the priority for vaccination, they're now the longest post-vaccination. And with Delta cases surging, is it really a pressing concern, in your opinion, to approve the booster dose, particularly for the elderly, as soon as possible?
Well, speaking as a member of the group, I damn well agree. And I don't agree with the ACIP putting off that decision. I think the need for the booster, particularly in the elderly, is obvious. And there should be a recommendation for it sooner rather than later.
Right. And on the other end of the spectrum, do you think that we should have plans to test vaccines in children more quickly after the adult clinical trials, given that most children are still unprotected against SARS-CoV-2 and we're going into a new school year?
Yeah, well, I have written an article with Ofer Levy on that point. And I do think that we need ultimately to make SARS-2 vaccination a routine vaccine for children. As you know from reading the newspapers, we have a large vaccine hesitant population among adults. And I don't see that, unfortunately, changing a great deal. So we are not going to have anywhere near 100% vaccine coverage. But if, as we do with other vaccines, start vaccinating children, and of course, the proviso is that they have a more permanent response. But anyway, leaving aside that question, I think that vaccination of children is going to become important, because I don't see the virus disappearing. If I'm wrong, that would be great. But if I'm right, we will have to look to the future and vaccinate children in order to create an immune population.
Yeah, absolutely. And I have one question here on whether it might make sense for people who haven't been vaccinated yet to delay the interval between the mRNA vaccines. So rather than doing them at the 3 to 4 weeks, but maybe at 6 months.
Well, the simple logic answer is yes, But then there's the issue of do you leave people susceptible during the interval between doses in the presence of an epidemic? So I would say on a practical level that you have to use the 4-week interval to vaccinate somebody who hasn't been vaccinated previously. But I foresee that ultimately we're going to have a third dose, which will be given approximately 6 months later. The data, and again, I have a paper in press about this. It's a principle that is true for all inactivated vaccines, that the longer the interval between doses, at least up to 6 months, the better response you get. And I did show a slide on that for the AstraZeneca vaccine, that the longer the interval, the better the response. But as I just said, of course, the practical issue that you want some protection early in the presence of the epidemic.
Absolutely, yes. Well, Dr. Plotkin, I am 100% sure we could keep you all day with questions, and we really appreciate your sharing all of this with us. And I know I promised I would let you go a few minutes before 11 because you have to rush to another session. So we will have to leave questions for another time, but maybe we can get you to come back. Thank you so much.
Well, thank you. I'm happy to do this, and good luck to the Human Vaccine Project.
Thank you. Thank
Bye-bye.
you so much. Bye-bye. I'd like to just thank all of our attendees for participating also in today's webinar and for submitting so many and such great questions for our speaker. We're really fortunate to have such an engaged audience for these lab meetings. And I'm very sorry we couldn't get to all the questions given Dr. Plotkin's schedule. But I do invite you to join us 2 weeks from today on August 12th for the next Global COVID Lab meeting. Our speaker that day will be Dr. Stefan Mueller, the co-founder, president, and chief scientific officer at Codagenics. His presentation will be on Covivac, a live attenuated SARS-CoV-2 virus for intranasal vaccination against COVID-19, which I think relates to some of the questions we had today related to mucosal immunity. And if you're interested in more research on COVID-19, please sign up for the HVP COVID Report, a bi-weekly newsletter that provides insights from experts around the globe and highlights the latest scientific articles and data. Finally, please visit our website and follow us on LinkedIn, where we will upload a recording of today's webinar. And with that, I will say thank you again for participating today. Stay safe, and we hope that you'll join us again on the next Global COVID Lab meeting. Thank you so much.